Hello, seniors. It is time for semester 2 final review for your Earth Science class
with your favorite teachers, Mr. Mozel and Miss G. This is your review. You do have a review sheet, so you can fill this in on your review sheet, or you can just listen and enjoy. This is question 1, three-parter. You got 3 things you got to define here for question 1. The MOHO, the continental drift hypothesis, and the plate tectonic theory. So let's start with that MOHO. The MOHO is basically the boundary between the mantle and the crust. That's all you have to know. It's just the boundary between the mantle and the crust. Moving on to the continental drift hypothesis. Evidence we know that the continents once were all together. There's 3 things. Ancient climates, the shape of Africa and South America, how they fit like a jigsaw puzzle, and also the evidence of similar fossils found on different continents. So those are the 3 things you should know for the continental drift hypothesis. Moving on to the plate tectonic theory. Basically, that theory states that the plates are constantly moving. They float on the mantle, and when they move, sometimes they crash into each other, and when they crash into each other, sometimes we get earthquakes, sometimes we get mountain building, and through that mountain building, sometimes there are also volcanoes. So that was question 1. Question 2. You guys should remember this. This was the S waves and the P waves. All you have to remember is the S waves are slow moving and they can travel through solids only, and P waves are fast moving and they can travel through liquids and solids. Measuring the epicenter, we use something called, and you've done this, you did this in class, we use the travel time graph, and that's using the S wave and the P wave to determine the distance of the epicenter. So what actually causes the fires during an earthquake? If you remember, the causes of the fire during an earthquake were from broken gas lines from the earth shifting. Question number 5. The continental crust is primarily made of this rock right here, and this is granite. Question 6. Where do new oceanic crusts form? They form along ocean ridges. This is a ridge right here. And it is destroyed right here. You see your oceanic lithosphere going down. And what forms there is a trench. Question 7. A volcanic island arc. Where do they form? They usually form where you have 2 ocean plates. You have one ocean plate here and one ocean plate here converging on each other. And that's a convergent oceanic to oceanic plate boundary. For question 8, how did the Hawaiian Islands actually form? They formed over a hot spot. So right here. That's your answer. Hot spot. That's where the Hawaiian Islands formed, over a hot spot. All right, question 9. We have this split up into 3 different parts. When we're talking about viscosity right here, viscosity is basically how thick or how much like a liquid lava can be. It's determined by the silica and other properties of the lava. So just remember, viscosity is how thick the lava can be. Right over here, this is pyroclastic material. This is just one form of it. Pyroclastic material can be ash, lapilli, or cinders. Right here we have our intraplate volcano, and it's pretty simple. Intraplate volcano is just a volcano that occurs in the inner portions of a plate, not at the edges. Question 10. The most violent volcanic eruptions come from this type of volcano, and right here, what you're looking at is a composite cone volcano. So when this volcano erupts, it will cause the greatest and most violent eruptions. Moving on to mountains. This one we couldn't find a good picture for, so we just kind of wrote them in there. 3 factors that affect the rock strength. You got time, you got rock type, and you got temperature. For question 12, our compression stress versus tensional stress. And When you pull something, you create tension. You're pulling apart. You're stretching it. All right. When you're compressing, just the opposite. You're pushing in. You're shortening it. You're compressing it. Okay. And these are a couple examples. Tensional stress causes a normal fault, and a compressional causes a reverse fault. Question 13. It says define the following. So we have normal fault and the process orogenesis. This is a normal fault. So if you can remember, the hanging wall falls down and the normal wall stays up, that is a normal fault. For the process of orogenesis, that is the process of mountain building. This is an example of that. Pushing in and mountains are formed. Question 14. An example of folded mountains, and what you're seeing here are the Alps. The Alps are a good example of folded mountains. That's how they were formed. Alright, here's question 15 and 16. Which stress forms folded mountains, and folded mountains form at what type of boundaries? So as you can see here, we have our folded mountains right here in the middle. We have two plates coming into each other, so when they come into each other, that is a convergent boundary, and also that's compressional stress. Two similar things, and that's how our folded mountains are formed. Question 17, another one that's broken up amongst 3 items. And we have 3 things here for you. I see we skipped some of them, so we'll come back to some of those other ones. Uniformism. Basically, uniformism, looking at this picture here, it's a rock strata demonstrates geological processes that are still occurring today that happened way back when, at the beginning of time. So the same type of processes are still happening in our world as they were back at the beginning of time. This diagram picture right here, this is a demonstration of angular unconformity. You can see we have our layers were laid down nice and flat. Then something happened where they're laid down in angles, and that's this angular unconformity. Down here, this is an example of correlation, and correlation means so sandstone was laid here at spot A and was also laid here at spot B. So if we know those were both laid at the same time, we can kind of get a general idea of the time frame when both were laid down in the history of Earth. Okay, number 18. This is also broken up amongst 2 slides here. We have a couple of different time frames in geologic time that we want you to know. We have the Phanerozoic era, which is right here. And this, remember, Phanerozoic means visible. Same thing with Cenozoic. We want you to know what that means. So Cenozoic means recent life. So there's a little diagram here. So Cenozoic is recent life. Over here is an example of the Precambrian times. Just remember, Precambrian is a period of Earth that we don't know much of. It is the beginning of life on Earth, but we don't have a lot of knowledge of what occurred back then because there were not a lot of fossils found because of soft bodies. The animals and organisms that lived during the Precambrian were soft, so they did not leave any fossils for us. Continuing with question 18, we have Gondwana and Laurasia, and what you want to remember about those is Gondwana was formed with South America, Africa, India, Antarctica, Australia, and Eurasia was more of your North America, parts of Asia, and Europe. So if you could look at that picture and understand that picture, you should do very well on that question. Question 19. So at the beginning of the Cambrian period, we had what was called the Cambrian explosion, and basically you can see all these beautiful looking organisms here. There was a big explosion, and we don't know what really happened. It wasn't like literally an explosion, but explosion of life. So all this life came to be in the oceans, and that's how the Cambrian period began. Question 20. So, when did Pangaea break apart? Right here, Mesozoic era. So just remember that. That's when Pangaea began to break. question 21, this should be easy. During the Mesozoic era, our dinosaurs right here, our friend T-Rex, they dominated that era. And our last question here for fossils in geologic time. The period we're in right now for the last 2 million years, it is the Quaternary. So greetings from the Quaternary.
The most important atmospheric gas is actually water vapor, which makes up 0 to 4% of the atmosphere at different locations. The most abundant gas in the atmosphere is nitrogen. As you can see in this slide, the clouds right here are down near Mount Everest. These are all the lowest layer of the atmosphere, which is the troposphere. Sleet is formed as a result of when frozen water up here in the clouds falls. It starts to warm up when it hits warm air, and then it melts. But then as it goes towards the ground, it hits an area of very cold air and it refreezes, falling onto the surface as sleet. Sunlight falls onto Earth through the process of radiation, but Earth has these gases that trap that sunlight. Those gases are called greenhouse gases. Carbon dioxide is the most well-known of these. So it traps some of that sunlight and keeps it in Earth, almost acting like a blanket, and keeps the Earth warm. So with global warming, as we release more carbon dioxide into the air, there is more carbon dioxide to make a thicker blanket, and then more heat is trapped and the planet begins to slightly warm. If you recall our lab on solar radiation, we took samples of soil and water and exposed them to light and took their temperatures. In this lab, we proved not only that land heats faster than water, we found that land cooled faster than water and was capable of reaching colder/hotter temperatures than water. This led us to understand that water is a mediator or moderator. It's going to control the temperature in an area. So if you are located near water, your temperatures will be less extreme and more pleasant all the time. We have used this picture before to explain to you the different types of clouds. Just to go back and review, stratus means layer. So stratocumulus clouds, stratus clouds, altostratus clouds, all three of those are layers of clouds. The prefix alto means middle. So clouds that have the alto prefix are in the middle of the sky. Those are altocumulus and altostratus. We also have the prefix cirro, which means basically wind whipped. So cirrus clouds are very high up in the sky where they can become whipped around like the wind. As a result, they look like feathers. You can also have cirrocumulus sky, which is very high up in the atmosphere, puffy clouds. With that, cumulus means accumulate. So cumulus clouds look like little piles that have accumulated, and a cumulonimbus cloud is an accumulating towering cloud. It gets the nimbus name for the fact that it contains rain, therefore it is dark gray. Cumulonimbus clouds also are the precursors of all storms. The storms develop up here in the anvil.
I just emailed.
Dew point and condensation tend to be a confusing topic. It doesn't have to be so. All you need to know is that as warm air rises into the atmosphere, it cools down. As it cools down, cold air can't hold as much water. At a certain temperature, that's the temperature it needs to reach in order to be cool enough to release water. So when that warm air reaches the dew point or the temperature needed for condensation to occur, that's when we start to see the transition from gas to liquid water. Air pressure acts equally on all sides of an object. So you will have an equal pressure up, down, left, right, any direction. We used an isobaric map to follow the differences in atmospheric pressure in high and low pressure centers. You will remember that we connected equal lines of pressure and found that the pressure changed over the course of the country from high to low. When the bars in an isobaric map are close together, that indicates that there is a quick change in pressure and therefore we'll have high winds. When those bars are spaced out far apart, it means that the pressure isn't changing as quickly. It has a much weaker gradient of pressure, so you will not have as much wind there. This is a middle latitude cyclone. It is simply a low pressure system in which the winds are circulating towards the center, as happens in any low pressure system. The winds are circulating counterclockwise, so remember, turn down for low. Also, you can see in this picture that we have a warm front followed by a cold front. As that cold front takes over the warm front, we develop an occluded front, and that is when a mesocyclone forms and we get tornadoes and hurricanes. One final point here is that as the air circulates in toward the center, the pressure decreases more and more and more towards the center, so it gets lower and lower and lower. A nor'easter is simply a cold version of a hurricane in a sense. It is a low pressure system, so winds are going counterclockwise. The difference here is that you have the maritime polar air mass as your fuel source. So you have ice cold, wet air coming from up north, and that is being swept counterclockwise. As a result, you have a lot of ice cold precipitation coming into an area. These are the major snowstorms that the northeasterners get in the winter. This is a picture of the mature stage of a thunderstorm's development. You will notice three very important things. First, we have downdrafts. Second, we have updrafts, that is warm, moist air rising. The downdrafts, again, were cold air that is coming down through the cloud. And as a result, you have lots of significant rain and hail and lightning associated. The anvil of the storm is going to point in the direction that the storm is moving. One interesting fact about thunderstorms, the reason that they're able to form hail is that hail basically is water that would be coming down as rain, but rather it gets stuck between the updrafts and the downdrafts, and it keeps going and going and going. Oh, here's a little arrow right here showing you. All right, so that's going to continue to circulate. So the rain is basically going to melt and freeze and melt and freeze and get up here and keep freezing, 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 freezing. It's just going to accumulate more and more water and then eventually fall as a large hailstorm. The major force behind hurricanes is the warm, moist air over the ocean. So if you take a hurricane and you move it over land, you basically remove the fuel source of that warm, moist air. So the hurricane comes onto land and two things happen. Number one, it has drier air that's cooler and is not going to fuel it. And then second, you have friction from the land slowing the wind down. So again, the fuel source is removed and the friction increases, and those together slow down and stop a hurricane. The major air masses which affect air in the northeastern United States, anything east of the Rockies as well, are the moist air mass at the bottom. That is a maritime tropical air mass, so it's warm, moist air coming up from the Gulf of Mexico. The jet stream, which is already highlighted for you, moves from west to east, bringing that moist tropical air up from the Gulf. Because of the rotating model of Earth, all air is going to move from a western direction to an east direction. Don't forget that's called the westerlies. The other type of air mass you really need to know about is the blue one up here. It is the cool air mass. It's coming from upper Canada. So this is the continental polar air masses. All right, just like the maritime one, these are going to be brought down and to the east by the jet stream. Some additional air masses you do need to know about include the maritime polar. As we just said, that does cause nor'easters up here. So the maritime polar air will come down and get rid of this maritime tropical air because the jet stream, which I can draw in for you right here, the jet stream will basically be forced down because cold air is more powerful. And so that cold air will come through and push the maritime tropical air out, and it will fill it with maritime polar air. You also need to know about the continental tropical air. We rarely get any of that in the eastern United States because of the CP air masses. So continental tropical air is hot and dry. We don't really get any of it, but it does cause the heat associated with the desert. This slide introduces you to the cold front and warm front concept. Simply, all you need to know is that a warm front is basically warm air moving into a cold area. A cold front is cold air moving into a warm area. And this, of course, happens around a counterclockwise situation. Okay, here it's time for my favorite catchphrase, and that is the frontal frontal wedging. So when a cold front or a warm front comes in, we basically get a wedge shape. So in this bottom picture, you have warm air coming into an area. It rises up over the cold air and creates this wedge shape. A similar situation when a cold front comes into an area, it's a little bit differently shaped frontal wedge, but it still exists. Also important on this slide is the location here of a thunderstorm. You can tell that by the cumulonimbus clouds, which are starting to tower up and become very tall. The cold front comes in, it takes over this warm area, so the cold front will replace the warm air with cold air. When that happens, the warm air is pushed up, and so as the air rises, it reaches its dew point and turns into condensation, and the stronger the cold front is, the worse and taller this towering cumulonimbus cloud will get, and the bigger the storm we will have. Down here in a warm front, you wouldn't expect a towering cumulonimbus because the warm air is gently being pushed up over the cold front. It will be gradual, and so it will simply go right up over the top. You might get a little bit of rain here, but it will not be a massive storm.